All right, so this lecture will be Lecture 4, Part 7, which corresponds to Section 4.8 of your text. And this topic will regard Newton's method. Newton's method is a technique for finding solutions to equations. So finding the zero crossings of a function. So how to solve high-degree equations using Newton's method. And not just high-degree equations, but say like functions which are composite of trigonometric, exponential, and polynomial functions. You can find solutions to those equations as well. All right, and you can find these solutions without the aid of technology such as a calculator or a graphing tool. So, for instance, suppose that a car dealer offers to sell you a car for $18,000 or for payments of $375 per month for 5 years. You would like to know what the monthly interest rate the dealer is, in effect, charging you. All right, so to find the answer, you have to solve this equation. So here's the equation. Don't worry about how it was derived. And so how would you solve such an equation? Okay, so that's definitely an example of a high-degree polynomial. So for a quadratic equation, ax squared plus bx plus c, we know we can use the quadratic formula to find the two solutions to this quadratic formula. All right, to this quadratic equation, that is. But for third and fourth degree equations, there are formulas for roots, like you probably picked up on that in algebra. They're somewhat difficult. It takes a lot of work to do them. And if f is a polynomial degree 5 or higher, there's generally just no such formula for computing its roots other than using some sort of synthetic division and Descartes' rule of signs and whatnot, something you may, again, learned in algebra. Then, of course, there are the transcendental functions, such as transcendental functions or the trig functions, the exponential functions. And how would you solve something like this? Cosine x equals to x. Okay? All right, so you can get an approximate solution by plotting the equations. But again, that would be approximate because how good is reading a graph? You would have to resort to zooming in and guessing, right? So for cosine x equals to x, I guess this would be what we're dealing with. You could see that the root is approximately 0.0076, but well, I don't know. This isn't cosine x equals to x. This would be that interest polynomial, I think. Okay, I'm not sure what this is, but what the point of the slide is showing that you would zoom in to find these particular roots right here. And good luck trying to discern what that number is. And especially the case if the solution is irrational. And then trying to read an irrational number from a graph is almost impossible to any degree of precision. So zooming in, yeah, and the zooming action becomes a laborious task. Then there, of course, there are numerical root finders, which is what Newton's method is. You could use a calculator root finder or a computer algebra system, and in doing so, you would see that the solution to that polynomial equation was this. Okay, so let's talk about Newton's method. Yeah, so Newton's method is generally the way that calculators implement root finding techniques, and it's an application of the idea of linear approximation. So how does Newton's method work? So it's a geometric argument. So suppose we're given a graph of an arbitrary function, which is shown in blue right here. So, and then we label, so y is equal to f of x, as shown here. And we pick an arbitrary point. Well, before we pick an arbitrary point, we see that we discern that a root of this function is at r, x equals r. And we want to try and discover what r is. So, we start off by, say, picking an arbitrary point to a reasonable guess near an arbitrary point on the graph that is reasonably close to this x-intercept. Okay, and so we call it x sub 1, fx sub 1. All right, and what we're going to do is we're going to calculate the equation of a tangent line to this arbitrary point on the graph right here. So we'll calculate the equation of a tangent line at this point of tangency, and we'll call it uppercase L. All right, so what does that offer us? Okay, now, first approach. Okay, so basically when we arbitrarily select x1, fx sub 1, the first approximation to the root we'll call x sub 1, right? But you can see x sub 1 is not quite r. So x1 is not quite r. So what we can do then is when we calculate the equation of line L, here's what follows. So we consider the tangent line L to the curve y equals f of x at this point we talked about, and we look at the x-intercept of L, label it x2. And if you notice that x2 is closer to r than x1 was, all right? So we have a better approximation to the root now. And what would happen if we, okay, so the tangent line is close to the curve, so its x-intercept x2 is close to the x-intercept of the curve, namely the roots. The x2 is close to the x-intercept of the blue curve, r, and as the tangent line is a line, we can easily find its x-intercept, of course. All right. That's why we compute the tangent lines, because we can find their x-intercepts of any line easily. All right. So what next? Okay, so we need to find a formula for x2 in terms of x1, and we know the slope of the line L is the derivative of the function at x1. So the equation of that red line is here. So this is the equation of the red line, and we've done this many, many times. Found the equation of the tangent line, and then all we need to do for x2 would be the x-intercept of this tangent line. So this of course is equal to the big line L, and so we have y minus y sub 1 is equal to f prime x sub 1 f prime of x sub 1 times x minus x sub 1. Okay, now it's easy to find the x-intercept. The x-intercept of this equation, of course, would be x2. Just set this y sub 1 equal to 0. Okay. Not quite. Oh, that's fx sub 1. Not this y sub 1, but the other y, sorry, wrong y. Y sub 1 is not 0. Y sub 1 is fx sub 1. We can't set that equal to 0. We set y equal to 0. So we have y minus f x sub 1 is equal to this. So to find the x-intercept, set this equal to 0 and solve for x. Okay, so we have negative f x sub 1 over f prime x sub 1 plus x sub 1 is equal to x. So this, which is effectively x sub 2. So that would be the x-intercept, right? And so that was easy enough to do. All right, that's probably shown on the next slide. So as you can see, they set y equal to 0, and then they solve for x2 just like we did. So here's the x-intercept, and we can use x2 as the second approximation to r. Then we can do the third approximation. So we repeat the procedure with x1 replaced by x2, and using the tangent line at x2 f x2. So the third approximation would be found by just replacing x1 with x2 and then x2 with x3, and so you get this iterative process. So we have what are called successive or iterative approximations, and as shown here. So here's the sequence of tangent lines that you compute. And in each step of the way, you see that the x of i's, as I grows larger, gets closer and closer to r. Okay? So you find the x-intercept, then you find it with the x-intercept, you plug it into the function to get a new point of tangency. Then you calculate a tangent line at the new point of tangency, find that x-intercept. Then that x-intercept becomes a point of tangency on the function. Okay, you plug this new x-intercept into the function. The coordinates form a point of tangency for a new tangent line, and so forth, until you get very, very close to r. So you walk toward the root of r. Okay, so what is the approximation? How do we know? All right, so in general, the nth approximation is x of n and f prime x of n is not equal to 0. Okay, so if the nth approximation is xn and f prime x of n, in other words, this denominator is not 0, then the next approximation is given by this. So this is the general form of Newton's method. Okay? And so where do you terminate the process? How far do you go to get to R? All right, so if the numbers x of n become closer and closer to R as n becomes large, then the sequence converges to R, and we write the limit as n approaches infinity of x of n is equal to R. Okay, the sequence of successive approximations converges to the desired root for functions of the type illustrated in the previous figure, of course. However, in certain circumstances, they may not converge. Okay, yeah, and here's a case where your selection of x of 1 won't converge to R. So for instance, look at their choice for x of 1. So they guessed x of 1, which is close to R, for the blue function, and then they drew the tangential line at the point of tangency, where x1 is the abscissa of the point of tangency. And then notice where x of 2 ended up. X of 2 is the x-intercept of the first tangent line. Then they calculate the second point of tangency, where x2 is the abscissa of this point of tangency right here. Then they drew a tangential line this way, and then x of 3 is the x-intercept of the second tangential line. And notice that if we try to evaluate the function at x of 3, there is no function. So in this case, Newton's method does what we call a blow-up condition. There's no further pursuit of the solution here is possible. Right, so that could happen with functions like this. So you have to be careful in your initial selection of x of 1. This is called non-convergence. All right, next slide. Yeah, so forth. Right, and then of course there are cases in which the convergence toward a root happens very slowly. In other words, you have to have maybe about 300 or 400 iterations of the Newton's method before you finally get to a root, or it may be that the number of iterations just never terminates. You just keep computing iterations forever and ever and never get close to a root of the equation. And so these exercises in your text will demonstrate that. All right, so let's see an example here. Let's find a root to the equation x cubed minus 2x minus 5. And we'll start with x of 1 equals to 2. And we'll find, so you want to find the x of 3, the intercept of the second tangential line. And we'll use x of 3 as the root approximation. So let's see how that goes. All right, so we apply Newton's method with f of x equals to the function x cubed minus 2x minus 5. Of course, take the derivative, so that's 3x squared minus 2. And, this is what Newton used, okay. So he chose x1 equals 2 after some experimentation because, so here's what motivated Newton to choose x1 equals to 2. He used the intermediate value theorem, okay. Remember the intermediate value theorem? That's what Newton used. So since this is a polynomial, we know it's continuous everywhere. And so Newton just found out that f2 is equal to -1 and f3 is equal to 16. So by continuity, the polynomial has to transition from output -1 to output 16. And along the way, it has to cross the x-axis at least once. Okay, so using the intermediate value theorem, he deduced that, so the root's going to lie somewhere between 2 and 3. And so now how do you calculate that root? Okay, so that's one way you can choose your initial selection for the root. Just use some sort of pre-processing technique like the intermediate value theorem, which is what your calculator does, by the way, if you have a root solve on your calculator. All right, so I guess we set up a table. Oh, okay, so here is the equation. This is a typo. This should not be written. The left-hand side is written incorrectly. The right-hand side is okay. This should not be x of n plus 1, but the subscript should be written as x of n plus 1. X of n plus 1 is the next x-intercept. So in this case, x of 1 was equal to 2. So you basically, here's your fx of n, okay, and here is your f prime x of n, okay, and then here's your x of n. And so don't do that. Use x of n plus 1, all right? So this is basically the Newton's formula for the solution, the root finding of the equation. All right, and so of course when n is 1, x of 1 is 2. All right. So for n equals 1, x of 2 is equal to x of 1 minus all of this. And then x of 1, of course, is 2, so you plug in 2 for x of 1, and you get x of 2 is equal to 2.1. All right? And so the question asks you to find x of 3. So then x of 3 then would simply be x of 3 would equal to x of 2 minus x of 2 cubed minus 2x sub 2 minus 5 all over 3x sub 2 squared minus 2. And of course, you plug in x sub 2 is equal to 2.1. And when you plug in 2.1 into this equation on the right-hand side, you'll get x sub 3, which will be the approximation, your solution. Okay? So that's how it works. All right, so slide 32. So x of 3, there you go. And so they found that x of 3 was approximately 2.0946. So this is accurate to 4 decimal places. Now, obviously, the solution, the root for this particular equation is an irrational number. And so this is something you could not do in your algebra class. When you use the rational root theorem, the problems that you solved in your algebra class always had rational roots. They never had irrational roots. So now is your first encounter of being able to solve an equation that has an irrational root without having to use a calculator. All right, so, and in general, the roots of most equations will probably be irrational. Okay, so what else? So yeah, so they show the geometry behind the first step in this. Okay, so f prime of 2 is equal to 10. The tangent line to y equals x cubed minus 2x minus 5 at 2, negative 1 has equation y equals 10x minus 1. Okay, so the red line is the tangent line at x equals 2, y equals negative 1, I guess. Okay, and so so its x-intercept, they calculate its x-intercept right here to be 2.1. So there's just the graphical portrayal. And then so the next step is what if we want to go to 8 decimal places using that Newton's method? So how do we know when to stop? Okay, especially in the case where you have irrational numeric solutions. So the stopping condition. Okay, so the rule of thumb is generally that we can stop when successive approximations, okay, agree to 8 decimal places. So there's a section, well, this is obviously an older book, so don't worry about doing exercise 37 in section 11.11. That's not until calculus 3. So when the succeeding values differ by a small amount, that's when you can really stop. Okay, so here's an example. Suppose we want to find the 6th root of 2 correct to 8 decimal places. So the 6th root of 2 is equivalent to finding the positive root of x to the 6 minus 2, right? So you convert the 6th root of 2 into a polynomial expression x to the 6 minus 2, because the solution, of course, is the 6th root of 2. So f prime of x, of course, is 6x to the 5th, right? And then you just set up your formula. So x to the n plus 1 is equal to x to the n minus, okay, so this would be, your, right here, this is your fx of n, and then right here would be f prime x of n. Okay, so there's your Newton's method. Okay, and so using the table of iterations, you see values for x2, x3, x4, x5, and x6, and so forth. Okay, and so so if you see the difference between x5 and x6, they're almost the same. They match to 8 decimal places. Now let me clue you in on where these numbers, how you can, an efficient way of calculating these numbers. The best way to deal with it is just to simply set up a table. Start off with this formula, the Newton's formula that you'll extract based on the function f. Okay, well let me pull down the slide. Show you a best practice here. So take your function and build your function like this, and then just create a table, kind of like what you did in chapter 2. So first column of your table will be x sub n, and then the second column of your table will be x sub n minus x sub n to the 6th minus 2 over 6 x to the n to the 5th. Okay, and then your first column could, of course, be n. All right, so this is n. So you have 3 columns, like so. And then just fill in the rows of the table. You can even use an Excel spreadsheet if you're familiar with this. So if n is 1, then x sub n we declared to be, what was it, what was x sub 1? 1? Okay, so they started out at 1. And then when you plug 1 into this formula, so n is equal to 1, so x sub 1 minus x sub 1 to the 6 minus 2 over 6 x sub 1 to the 5th. Okay, so that came out to be this number right here. Okay, so that was, see if I can pull it down. Let me arrange stuff here. Okay, so when you plug 1 into this equation, you'll get 1.166666667. Okay, now, so you filled in this first row. Now you plug in 2, and x of 2 is, you take 1.166666667, and you feed it into the formula, and you'll get 1.126444368. Okay, and this will be your x sub 3. So then 3. So you take this number, put it here. Okay, and then you feed it into the formula, and then you'll get x sub 4, and so forth. So you can organize this information in a tabular approach to help you visualize the evolution of the solution. That would be the iterative process. Okay. All right, so slide 40. Okay, so correct to 6 decimal places the root of the equation cosine x equals x. So reformulate the expression into an f of x style. So f of x, which is equal to cosine x minus x. Then f prime of x, of course, is minus sine x minus 1. Not sure why this won't let me scroll. Okay. All right, and then so we build our Newton's table. Here's our Newton's formula for this particular function. X sub n plus 1 is equal to x sub n minus all of this. And then they simplify it. So here's your Newton's equation. I'll call this the Newton's equation. And then you just fill in the tabular values. Okay. And so the question is, what's a suitable starting point for x sub 1? And you can do that by simply graphing. Okay. Now remember, a graph will only give you an approximate solution, not a solution to within 6 digits. Obviously, you cannot read a number correct to 6-digit places on a graph, unless I guess you really zoom in. I guess the newer online calculators you can, but it's still going to be quite challenging and computationally slow on a website to do so. So anyway, you can see a good estimate to where the root is right here, where these two functions intersect would be, say, x equals 1. So that would be a good starting point. Okay. So x1 equals 1, and then filling in the tabular approach, you'll see these successive approximations. So X4 and X5 agree to within 6 decimal places, and 8 in fact. So you would have to conclude that this is converging. So the solution at cosine x equals x happens at x equals 0.739085. Try reading that from a graph. Not very easily done. Okay, may not even be possible. Strange, I have to erase that to use the scroll bar. Okay, 44. Okay. Okay, all right, so yeah, you can use graphing techniques. Okay, we could have also started at 0.75. Okay, and that means you can, depending on how high resolution your graphing tool is, you can use fewer iterations. Yeah, so if you require ultra-precise answers like 6 or 8 decimal places, then a graphing technique may not be the correct approach because of the constancy of having to zoom in. Okay. All right, so that's the topic for Newton's method. So please, I think there are a couple of web assignment questions out there for you to do, and I'm pretty sure there'll be 1 or 2 questions on your Chapter 4 exam involving this technique. So please stay current and try and solve problems using Newton's method. So that would be it for this topic. This would be topic 4.7.